Hello everyone, this is In Ho Jung from Seoul National University, South Korea. First of all, I want to thanks to the conference organizer to invite me as a keynote speaker. The title of this talk is Challenges in the Phase Diagram Study of the Alkali Oxide System. In this talk, I want to share our experience on the phase diagram study with you. Our research group has developed the FACSAGE thermodynamic database using CaO-CaF methodology. For the CaO-CaF type of the thermodynamic database, we evaluate all existing phase diagram and the thermodynamic property data simultaneously and critically, and prepare the one set of the Gibbs energy functions based on the most reliable experimental data. In this the process, phase diagram information is one of the most essential data for the good thermodynamic database development. This slide shows you the steelmaking consortium project we have carried out since 2009. Over the many years, we expanded the thermodynamic database toward alkali oxide, oxyfluoride, manganese and titanium and vanadium containing system, and also rare earth oxide system. In many cases, the phase diagram information for this system in the literature are insufficient. So we have to perform our own phase diagram study to assist the thermodynamic database development. In our lab, we have the many high temperature furnaces designed for the phase diagram study. And we also use the thermal analysis equipment. And recently, we developed our own solution calorimeter, which can be helpful to measure the standard enthalpy for the compound and the solution phases. And in many cases, we also use the so-called sealed platinum capsule technique for the phase diagram study. Now, this is the list of the challenges in the phase diagram study I would like to share with you today. So I'll go through one by one of this kind of the problem. The first challenge is the long incubation time. In many cases, we can perform the phase diagram experiment within several hours. However, if you do the phase diagram experiment at the solid state and also very acidic slag region, the incubation time takes much longer. This is the example for the P2O5 SiO2 binary system. As you know, both P2O5 and SiO2 are the network formers in slag. So the diffusion in this system is extremely slow. For example, the sample shown here is SiO2 and the liquid. So here, small tiny tridymite and the glassy phase can be seen. And we could get homogeneous sample like this only after 7 days at 1200 degrees Celsius. As you can see, the composition of the various point in the glass is almost same, so we could confirm that this sample is reasonably homogeneous and reach to the equilibrium state. And the sample here, for example, at 950 degrees Celsius take 73 days for the equilibration experiment. Another challenge is the volatilization of the sample during the phase diagram study. For example, P2O5 is the very volatile species, and this shows you vapor pressure over the P2O5 from 0.01 atm to the 1 atm pressure. So for the long time experiment, P2O5 can be evaporated, and the composition of the original sample can be changed. And this caused the misinterpretation of the phase diagram result. This is another example for the volatilization problem. Alkali oxide has also high vapor pressure, so the phase diagram in the alkali-rich region is very scarce. We tried the DSC experiment for the K4SiO4 sample, and during the experiment, we found out the loss of the weight loss, and also found very strange peak like this, which is not matching with the existing phase diagram. After the experiment, we examined the platinum crucible. As you can see here, the K2O is evaporated and the part of the sample is coated at the mid of the platinum capsule, and the rest of them is remained in the crucible. We can think that the main peak of the, the TTA coming from the bottom of the platinum crucible. So this part should be main source of the TSC peak in this case. Then we might have to consider composition of the material can be further changed than the TJ correction. So for example, in this case, we can think that the composition even drift toward the more SiO2 rich region. So when you have this kind of the evaporation problem, it is very difficult to find out what's the original composition of your sample. So you can easily make a mistake in the phase diagram study. So in order to tackle this kind of the vaporization problem in many oxide and oxyfluoride system, we developed a special technique to use the sealed platinum capsule for both furnace accumulation experiment and DSC or TTA experiment. Now I will show you briefly how to prepare the starting sample containing in the sealed platinum capsule. The first is the choice of the noble metal crucible, and we are typically using platinum, gold, or gold palladium tube. Then we cut it out about 1 centimeter in length and anneal it at about 1000 degrees Celsius to remove all the impurity attached on the tube first. Then we flatten the one side of the crucible and weld using the micro welding machine. We anneal the platinum again and remove the impurity or moisture which can be induced during the welding. Then the starting sample prepared separately is the packed inside of the crucible. The other side of the platinum crucible is also welded. In order to check the integrity of the welding, we do the leakage test using the sonication in the water and measure the weight change before and after to confirm the leakage. If the PT capsule passed the sonication test, we put the capsule to the DTA DSC or high temperature annealing furnace for the failure study. Depending on the experiment, the shape of the platinum capsule could be slightly different. The image shows the sample before and after of the experiment, and we do weight check again after the experiment to know whether there was any leakage during the experiment or not. When the sample has a very high vapor pressure, bloating of the capsule can be observed like this. But because of the platinum capsule is small enough, we typically see the homogeneity in the equilibrium phase inside of the capsule. This shows you one of the examples using platinum capsule. As you see, no weight change over the 3 cycle of the TTA experiment here. And the sound and the consistent thermal peak can be obtained in this way. Using this sealed platinum capsule technique, we could obtain good phase diagram data. For example, this is K2O SiO2 binary system, and this eutectic temperature was the first time measured by using this kind of the sealed platinum capsule. Next challenge is the hygroscopic problem. Many alkali oxide and fluoride and P2O5 can easily react with water and form hydroxide. This can induce the mistake in the phase diagram study. So for example, this is K2O Al2O3 binary system here. And two groups of the people reported a completely different melting temperature in the high Al2O3 region. So for example, Moya and et al. Reported that they found the liquid phase above the 1450 degrees Celsius, and the Ross et al. Mentioned that they found the liquid phase only at above the 1910 degrees Celsius. So in order to resolve this kind of the inconsistency, we performed our own experimental phase diagram experiment using the sealed platinum capsule again. And we took the composition of the 0.6 of the Al2O3 and performed the DTA experiment. As you can see in this experiment, we don't see any strange peak at around 1450 degrees Celsius. So we can say that the group of the data which reported low temperature melting is the strange. Then we prepared another sample equilibrated at the 1500 degrees Celsius, and we polished the sample after the experiment for the EPMA and the XRD analysis. This is the photo image for the surface of the polished sample left in the normal lab atmosphere. As you've seen, over the 20 minutes, the material is react with the moisture in air and completely hydrated, as confirmed in the XRD data. So this kind of the hydroxide hygroscopic problem can mislead conclusion in the phase diagram study easily. And the next example is the hygroscopic problem in the Li2O ZRO2 system. In the thermodynamic database development, we found out that phase diagram data reported here and the thermodynamic property data is not consistent with each other. In particular, the deep eutectic region here cannot be reproduced. So we performed our own DS experiment using platinum capsule again. Surprisingly and unfortunately, we got the same result as the previous phase diagram study. So as you can see here, this peak is corresponding to the deep eutectic peak in the previous phase diagram. However, when we analyzed this DSC data more carefully, we found something strange. So if this is the eutectic peak, we should expect much large peak than any other peak position here because of the melting. However, this is very small. So we did many other analyses, including the in situ XRD, and found out that the small water in the isopropanol alcohol when used in the sample preparation can contaminate the sample and make a hydroxide. And this hydroxide, unfortunately, cannot be evaporated during the pre-annealing treatment at 800 degrees Celsius, and this can induce the strange phase diagram like this. So we changed our alcohol to the so-called cyclohexene, which containing zero amount of the water. Then we could get the consistent and very good phase diagram data. So in all these cases, we found that the peak is matching very well with eutectic actually, the temperature reported early. And so in some cases, very small amount of water contamination during the early sample preparation stage can change the phase diagram information at high temperature. The next challenge is the quenching of the sample. If the sample, especially liquid sample, has a very low viscosity, it is hard to quench it. In fact, in the most cases, we can find homogeneous and very fine quenched crystal formation like this one or like this one. From the morphology, we can easily tell that this is originally liquid phase. In some cases, EPMA area mapping may not give you the accurate composition analysis due to this kind of the small quenched crystals. So we have to be careful about the composition analysis when you have the quenched crystal. Of course, XRD cannot be used in this case because it can give you the wrong phase analysis result. The next challenge is the EPMA composition analysis. Of course, EPMA is the extremely useful technique for the phase diagram study, but it cannot detect lithium, and sometimes other alkali content and the fluoride content may not be accurate. Then we have to prepare our own standard sample for the analysis and confirm our analysis result. This is the lithium oxide cases. We confirm the equilibrium phase both by using XRD and EPMA elemental mapping. As lithium is not detectable, we prepared Li2SiO3 and spodumene sample as standard and confirm the lithium content by using this kind of the simple strategy. So basically we assume that we check first EPMA count, and if it's about 100%, we assume that the EPMA itself is working well, and then based on the amount of the other actually element count, we can estimate what's the amount of the lithium, for example. And also, when you actually go to the other alkali oxide or fluoride, because of during the beam analysis, some of this element can be evaporate or migrate. So you have to find out the good beam analysis condition. The next challenge is the crucible material itself. We have to choose the proper crucible material which is inactive with the sample we want to study. For example, this is the tin oxide system. We had difficulty to use the thin platinum capsule due to the high vapor pressure over SNO. So we paired always the high temperature experiment at around 1600 degrees Celsius or 1650 degrees Celsius. So we try to use the rhenium crucible, which is reported in the literature. After about even 10-minute experiment, we found out that rhenium is reacting with a tin oxide, and we assume that this kind of the chemical reaction happen. And because of this chemical reaction, the rhenium can be seen inside of sample. And also we believe that the oxide sample is also contaminated by the rhenium oxide. And this kind of actually the contamination mislead your phase diagram analysis. As you know, platinum is not the mighty solution for the crucible material. For example, PT can easily react with iron to form the FCC solution or order the phase like this, as shown in this phase diagram. So I performed the thermodynamic calculation, iron oxide with platinum at the reducing condition. You can find out that iron platinum FCC phase formation, and then iron 2 plus can convert partially to the iron 3 plus during this kind of the chemical reaction. So the platinum can be used only for the certain condition, and same for the other crucible material. And another example is the lithium oxide rich sample. So when the lithium oxide rich sample, especially when lithium oxide is higher than 60%, then lithium oxide can also react with the platinum. And so we have to change the platinum capsule to the called palladium capsule in some cases. The last challenge I want to mention is the gas dissolution during the phase diagram experiment. We can do the phase diagram study sometimes at the open gas atmosphere because there's almost no vaporization problem. But when we target the composition at the high basicity region, the melt can dissolve many gas species easily. For example, this is the CaO-CaF₂ binary phase diagram study. The reported liquids of the CaO here is completely different from the study by study. So one group mentioned that the liquids line is like this, the other, and this is the third group. And these two groups used the open capsule experiment, and they used the different type of the gas atmosphere like this. And during the experiment, this gas can be dissolved into the CaO saturated liquid phase. And however, in this case, we use the sealed platinum capsule to prevent any kind of the gas reaction. In this way, we can get the good liquidus data, which is consistent also with thermodynamic data. So you have to be sometimes careful when you use the open crucible, especially at the very basic oxide region. This is the summary of the talk. I wish you can pause the video for a couple of minutes and read it through and get our hands-on experience and advice from this talk. I hope this talk is helpful for your future paradigm study. Thank you very much and enjoy the rest of the conference. And if you have any question, you are very welcome to contact me anytime. Thank you.